All right, the next organic family we're looking at is carboxylic acids. Now, a carboxylic acid has a functional group that actually doesn't have a name. So there's no name for this functional group, but it's a consists of a end carbon that has a double bonded oxygen atom and a hydroxyl group. Okay, so whenever we see this on the end of a carbon chain, you know you have a carboxylic acid. If you took 4U biology, you probably are pretty familiar with the carboxylic acid, really important in protein synthesis. So when we're naming organic molecules that have their carboxylic acid functional group, it gets the endoic acid. So for example, we look at this very simple carboxylic acid, 2 carbons, tells us that it's eth, and it's a single bond, so it's ethn, and then oic acid to indicate that we have this double bonded oxygen and hydroxyl group bonded. So just making sure you have this copied before we move on. All right, we'll look at a couple examples of our carboxylic acid. For example, just going through some of the stages for naming. We've got 3 right here. And basically, when we go to name our carboxylic acids, you count your number of carbons. 1, 2, 3, 4, 5, 6. Gives you the prefix hex. All single bonds for an. And then we see this tells us that it's a carboxylic acid, so hexanoic acid. If you've got a double bond, then like we see right here, then we have to change right in here to indicate that double bond, propenoic acid. Now, there's only one location for the double bond, so we don't have to indicate position when it's prop, because it could be here or here. And then if we move the double bond here, this is still this becomes carbon. Sorry, no, I'm going to retract that. It doesn't really, the double bond can only go here because this carbon cannot make a double bond with this carbon. And then if you happen to have a hydrocarbon chain that has an alkyl group, we just name those how we would normally. So this is 2-methyl. The carboxylic acid goes on carbon number 1. And then this is obviously carbon number 2. So this becomes 2-methylbutanoic acid. And then here is a slightly more challenging one because we have our double bonds. I want you to note that the carboxylic acid takes position number 1 here. Okay, so it becomes carbon number 1. And so 2, 3, 4, 5. So that gives us our penta. And we give position of our double bond. So penta 2, 4 di-N for 2 double bonds. Oic acid for the carboxylic group at the end here. And carbon number 4 also has a methyl. So we just add our branch chains like we normally would, giving the carbon that has a carboxylic acid group on it preferential in numbering. All right, so the carboxylic acid, by adding this double bonded hydrogen and a hydroxyl group, results in a very polar molecule capable of hydrogen bonding. Right, that hydroxyl allows for a lot of hydrogen bonding. So because of that, it has some very specific properties. Now, it's an acid, and so because it's an acid, it's going to turn blue litmus red, just like you've learned in previous chemistry classes. If they're a short chain carboxylic acid, they're soluble. But if it's a longer chain carboxylic acid, they become less soluble because by adding more carbons and hydrogens, you're adding more non-polar. More of the molecule becomes non-polar, and the ability to hydrogen bond, the whole thing kind of diminishes as you add carbons to the chain. And again, it has high melting and boiling points, and the longer the carbon chain, the higher those melting points will be. The high melting boiling points are to do with that very polar double bonded oxygen and hydroxyl group capable of hydrogen bonding. For our chemical properties of our carboxyl group, they react like an acid. So they'll undergo neutralization. They'll undergo a reduction reaction to convert back into an aldehyde. And they have reactions with amino groups to make an amine in protein formation. And this is kind of coming next, your next lesson. You'll be very familiar with this here if you've taken 4U biology already. And the other thing that they do is they react with alcohols to form esters. So our carboxylic acids are involved in a lot of reactions. What we're going to do is look at how we can form a carboxylic acid. And so actually make sure you got these properties down. So when we're forming a carboxylic acid, it happens in two different steps. So the first step is that we have to have an alcohol that undergoes oxidization to make the aldehyde. So the same reaction we saw in our previous lesson. And then the aldehyde undergoes another oxidization to create the carboxylic acid. And so it looks like this. We're going to look at ethanol. So ethanol, our alcohol here, reacts with that oxidizing agent. We kind of talked about the necessity of that before, and makes the aldehyde. Now, a carboxylic acid cannot form from a ketone because it has to go on an end carbon. So our ethanol will undergo oxidization and make ethanal, just like we see right here with an oxidizing agent we've mentioned before, KMnO4, the dichromate in H2SO4, either one of those. Okay, and of course it releases water. But then the aldehyde, the ethanal, will undergo another oxidization, and it does that. And when it does that, it results in the carboxylic acid, the ethanoic acid. So an oxygen here comes down and bonds in this space, creating the hydroxyl group. So our carboxylic acids have a lot of applications and uses. So a couple that you're familiar with is vinegar, which is everybody probably has in their kitchen. And its actual science name is ethanoic acid. Lactic acid in sour milk and yogurt, citric acid, and vitamin C is ascorbic acid. Okay. Okay, so I'm going to have some practice for you to look at naming our carboxylic acids, but they're really straightforward because all you're doing is naming that parent chain right here and then adding the ending oic acid at the end. Okay, so that's it for carboxylic acids.